So we talk about plasma. Apparently, this is very different from the state of matter, which is made of molecules, you know, of on Earth. So where can we find regions with lower temperature and denser materials in the universe? And I will not wait for the answers. So the answer is clear. It's in the nebula. So nebula will be the material thrown away by the supernova explosion or planetary nebula. So anything that's thrown away from a dying planet, a dying star to the universe, when they are diluted, they are also called interstellar cloud, which means they are far away from forming a star. They are just distributing dilutely in the universe. They have lower temperature, and they can form chemical reactions. And you can find the state of matter that you are familiar with: solids, liquids, gases. So this is the place where life can form. Okay, so it's boring now. I will just read through, sorry. So based on the mechanism of formation, there are planetary nebula, which our sun will form in the future, supernova remnants, and other nebula that gradually condense from floating gases, ice, dust, also called diffuse nebula. And based on the mechanism of illumination, depending on how close the nebula is to a star, they can be classified into emission nebula. A nebula gas is ionized by photons emitted by nearby hot stars. Or reflection nebula, nebula gas is not ionized by the stars, it just reflects the light. Or dark nebula, nebula material so dense as to obscure starlight. So we just see some photos. This is the place where light forms, or molecules forms. Orion nebula. So it's a diffuse, I can't control the light. Right, thank you. Thank you. Okay, Orion nebula, 猎户座大星云. It's a diffuse emission nebula, and you see this kind of photo in the video we watched 2 weeks ago. And this is the most popular image from the Hubble telescope, Eagle Nebula, 老鹰星云. And this is just part of the Eagle Nebula, and it has a name called Pillars of Creation, 创生之柱. So it's a little bit like you see in some science fiction. So it's a very weird but fantastic image. It's a diffuse emission nebula. And Ghost nebula, it's a diffuse reflection nebula. So it just reflects the lights from nearby stars. And this is Horsehead nebula. It seems like there's nothing here, but actually the material here is so dense that it obscures the starlight beyond. So it's a dark nebula. Okay, and chemical analysis of nebula composition. I don't know if maybe some of you have paid close attention to the video 2 weeks ago. How do astronomers analyze the chemical composition of cold objects in the cosmos? For the star, we know we can use optical telescope, 光学望远镜. The question is, for a nebula which is cold and it does not emit any light itself, how do you know its chemical composition? Any of you know the idea? It's introduced in the video 2 weeks ago. Forgot it. Idea? Sorry? Longer wavelength. Longer than infrared. Sorry? 什么 Redshift? No. Longer wavelength. Alright. The answer is radio wavelength. How long is the wavelength? Take a look. This is the infrared you talk about. It's optical. Visible light is here. Infrared, Ethan just talked about. Microwave is here. And radio wave is here. And how long is radio wave? Here. Wavelength in meter, 1 meter to 1,000 meter is its wavelength. So they need to use radio telescope to analyze the chemical composition of dark material in the space. So it's very different from the optical telescope used to study stars. And it operates in the radio frequency. So as you see the next slide, portion of the electromagnetic spectrum here. And molecules, they emit specific electromagnetic fingerprints. So I don't know if you still remember in the video, there was a scientist saying that they use the radio telescope and scan the sky to look for water. And then they realized that water is actually everywhere. So, water. Detection of water in a remote galaxy by radio telescope in 2008. So using this radio telescope, what has been known about nebula composition? So interstellar clouds are consisted of mostly ice, which is actually frozen volatiles. Volatile means 挥发性物质. But they also contain dust. Dust actually means oxides and metals. And that means most of the existing interstellar clouds are made of materials ejected during stellar evolution, and they are not from the virgin interstellar clouds after the Big Bang, because virgin clouds will have only hydrogen, helium, trace amount of boron, beryllium, etc. But most of the interstellar clouds have oxides, which contain magnesium oxide, for example, or silicates, and metal, which means iron. Which means all the material has undergone stellar evolution. Okay, and unusual condition of interstellar clouds, because during the discussion of Ray's presentation, he mentioned solar wind, 太阳风, which is actually a kind of stellar wind. For the sun, it's called solar wind. So what is solar wind? The state of matter in stars is mainly plasma, as we just said. And the protons and electrons in the upper atmosphere of stars get accelerated by the high temperature, because all stars are very hot. At some point, they reach the stellar escape velocity, because the plasma there, they are hot and they get accelerated, and at some point they can escape from the sun. And but the mass lost in the form of stellar wind is negligible, very small, compared to the total mass of the star. However, bombardment of the high-energy particles onto interstellar material is important for the formation of molecules. So the star also helps the formation of molecules by ejecting plasma. And in addition to plasma, the sun also gives interstellar clouds UV radiation. stars have high temperature, and the wavelength of black body radiation decreases with increasing temperature, which means increasing temperature, then it will emit short wavelength electromagnetic wave with higher energy, like UV. So, strong UV radiation can ionize chemical species and even break them apart. So UV radiation is actually very important for example, for the sun. For example, sometimes you see 某些广告牌 they fade away after long time of exposure under the sun. This is because of the UV radiation emitted by the sun. They break down the plastic molecules of the board, so the board will look faded and then get very brittle. That's because of the UV radiation. So the sun helps the formation of molecules by ejecting plasma and emitting UV radiation. Okay, summary. Interstellar clouds are the largest factories of molecules, and organic and inorganic compounds can be formed. So I didn't talk about organic. These molecules are raw materials for planetary systems. Now we come to the part that Ray discussed, solar system. And you have watched the video. And we discussed about the orbital movements. Let's review again. Orbits are not true circles, as said, ellipse. All planets lie close to the plane of an ecliptic, coplanar, 共面的. And the plane of ecliptic 就是黄道面. All planets rotate in the same direction around the sun, all counterclockwise, and the planets closer to the sun have shorter orbital period. So this is because of the conservation of angular momentum, as Ray mentioned in his slides. 角动量守恒. The orbits of planets are regularly spaced, so their orbits do not cross each other. I will skip this one. This one is not so important. Okay, and Ray also introduced a similar graph, planet size. Okay, outer giants, gas giants, and inner terrestrial planets were really small. So, as earlier scientists would say, is it a coincidence, 巧合, or is there a reason? Then you know, of course, there's a reason. And in fact, the model that we are going to talk about today is proposed in the 18th century by Kant-Laplace. And it says, this clear organization of the solar system gave rise in the 18th century to the nebular hypothesis. This is the hypothesis to explain the origin of the solar system, nebular hypothesis. And it's proposed by these two scientists. They suggested that the planets and the sun form from a single spinning flat cloud, from one cloud, interstellar cloud. And the spin of the planets and the existence of the ecliptic conform to, agree with, the original plan and the spin of the cloud. Because if everybody spin together, there will be a plane. And this plane is called the ecliptic. So that's the model. And now we will review the evidence. The first evidence, as we already see, is the orbital movements. And then Ray also talk about planetary density. And then fellas talk about planetary composition. We will quickly go through this. Density. Ray already talked about this mathematical expression, but he did not explain clearly why he should talk about this mathematical expression. Okay, the scientific question is, how do you know the volume, because you want to know density. How do you know the volume and mass of a planet? Let's see. Pin Zhen. All right, Pin Zhen. How do you know, how do you measure, can you imagine? How do we measure the volume of a planet? Any idea?
I don't know.
You don't know?
Because use the radius of the planet.
We know we can often see Saturn or Jupiter from the sky. Of course, you can measure its radius. But does that mean the radius you measure is true radius? Is it that small? Of course, what you measure is not a true radius. So what do you really need to measure in order to get the correct radius? You have learned from this. Any idea? How to measure the correct radius of a planet so you can calculate its volume. You have learned this in the week of Big Bang. Idea? This is the planet. It's actually 20 centimeter height. But I watch it from here. To me, it's only 2 centimeter high. So how can I analyze its true height when I'm standing here? Okay, Eden.
Absolutely brightness.
Sorry.
Absolutely.
But the planet, it does not have a real, its own light. When we talk about the brightness or something, you actually need to measure one critical parameter, which is distance. Distance. Exactly. Distance. So you need to measure the distance. And in the solar system, it's not that difficult because all the planets are very close to you. So you can even use the annular parallax. Alright? 年视差就是用那个地球转绕着那个太阳转的那个直径去当基线的那个三角测量。Okay. Very good. So you need to know the distance. Then you can estimate its radius. Then you can estimate its volume. Okay, that's the first step to measure density. But you also need to know the mass. How can you measure the mass of something bigger than you? Okay. Then what Ray was talking about is the Kepler's law, which actually says the mass of a planet can be determined from the gravitational influence it exerts on the orbits of its moon or on neighboring planets, which means if, like a Saturn, we know it's very large, and it has a moon next to it, then the moon movement of the moon is actually affected by Saturn. And then you can make use of this relationship to calculate the mass of the planet. So the MP is the mass of the host planet, R the distance at which the moon orbits the planet, V is the velocity of the moon, and G is the constant of gravitation. So you can estimate this. Then you can estimate the mass. As we know, Jupiter and Saturn, they are very fat. But actually their density is low. So especially Saturn is, if you put it on the water, it will float. So it's really light. Okay, implications. Outer planets are considered to have something lighter. And then consider the material in the interstellar clouds, which is ice, which is condensed volatiles, oxides, metal. Then you probably can guess what would be the major substance in the outer planets. And the inner planets are made of something dense. And also, normally elements in the upper row of the periodic table, 就是周期表上排, have lower density than those in the bottom rows. And interstellar ingredients, including ice, oxides, and metals, also have distinct densities. So when you have densities, you can base on these information to make some guess what might be the component in that planet. And when we talk about ice or oxides or metal, what exactly are we talking about? So we actually talk about methane, ammonia, water, silicates, magnesium silicates, and iron. That will be the substance we will talk about. And this is their density at 1 atmosphere. Okay, and you can see that their melting point, because let us talk about volatile. When we talk about something volatile, we look at their melting point. If the melting point is low, that means this substance is volatile. They can become gas at low temperature. You see that ice has low melting point, so they are volatile. Therefore, they might be the main component in that planet. So, outer inner. Composition. Okay, so far everything is not circumstantial, 就是间接的. Okay, how can we have something more solid evidence? So, evidence from the Earth. We know the Earth, the rock from Earth's surface has a density of 2.7 to 3 gram per square centimeter. But the average density of Earth is 5.5. So it's heavier. Where are the dense material? The answer is from the meteorite. Meteorite is 陨石, okay? And it's a piece of debris from sources as asteroids or comets. Okay, these terms looks very confusing. Meteorites does not infer the origin, 就是不涉及这个陨石的来源. Anything that falls from the space to the sun, to the earth, are all called meteorites. But asteroids in Chinese is called 小行星. Therefore, it means debris coming from the asteroid belt. 的小行星带，小行星带是在那个 is between the inner planets and outer planets. Is about at the position of the cross line. 小行星带. And comets has a even larger orbits than Neptune. Therefore, you remember Halley comets. They are probably the real outer margin of the solar system. 它是这个彗星的这个轨道是太阳系真正的边界。Okay. And it's still affected by the gravity of the sun, but its orbit is much larger. So comets and asteroids. And they can form debris too, which is called meteorites. And then, so meteorites are from asteroids or comets and survive its impact with the Earth's surface. So we can have remnants. Meteorites is a very important part of geochemistry because, as mentioned during Fella's discussion, meteorites is a material that is not affected by the Earth. Okay, question. What do you mean by affected by the Earth? The answer is by plate tectonics. Meteorites do not, or most of them are not affected by plate tectonics. So let's look at the detail. First, we know that you can do some dating, 定年 of the meteorites, and then direct age measurements show that they are really old. They are as old as the Earth, and many meteorites have unusual texture which can only be formed. So outside planetary environments, most meteorites are solids from the solar nebula, and they have not been accreted into planets. Because they have not been in a planet, they have been always at a low pressure environments. And these are the types of meteorites. We have chondrites, 球粒陨石, and under chondrites we have ordinary chondrites, 正常陨石, 球粒陨石, carbonaceous chondrites, which is a Thales carbon chondrite, 碳质球粒陨石, achondrites, 非球粒陨石, and iron meteorites. And actually, this will actually tell us about the chemical composition of the Earth. This is chondrules, 陨石球粒, as you see. Its mineral grain is spherical. So meteorites with chondrules is chondrite. And under optical polarized light microscopy, you will see it's very colorful and beautiful spherical mineral grains. So it's easy to identify. You will never see this in any rock on Earth. And the chondrules are once molten rock droplets, and which condense under very low pressure of space, and represent pristine material from the solar nebula. And ordinary chondrites is most of the chondrites is 22% of total finds. It's mostly rock, silicates with low iron and carbon contents, and it has high temperature mineral phase. Carbonaceous chondrites has organic carbon. In fact, scientists already found amino acids in carbonaceous chondrites. 他们有发现氨基酸. And it has high and low temperature mineral phase. And you see there's a good agreement between carbonaceous chondrites and sun. I will skip this. And I asked fellows what's the difference between ordinary chondrites and carbonaceous chondrites. And the answer is volatile components. So here there is a comparison. Here, the volatility coefficient is actually this ratio. This ratio means the content of one specific element in ordinary chondrites versus content in carbonaceous chondrites. So if it's 1, that means they have equal content. If it's more than 1, that means these elements is enriched in ordinary chondrites. Lower than 1, it means it's depleted, it's enriched in carbonaceous chondrites. So you see, carbonaceous chondrite actually enrich a lot of elements compared to ordinary chondrites. And why this is the case? This is because the volatile components, they accreted at low temperature and in materials like carbonaceous chondrites. Okay, after chondrites, we talk about achondrites. It's 8% of total finds. Achondrites do not have chondrules, so this is a photo of achondrites. Don't you think this is just a piece of volcanic rock? You can barely see, based on my observation, I cannot tell it's a chondrite. So they do not have chondrules. It may have chemical composition comparable to chondrites, but have texture similar to igneous rock on Earth. So to me, it looks like just the igneous rock. It's difficult to identify. So to be honest, I don't know how they can tell this is a chondrite or this is a meteorite. I don't know. They are formed in the interior of larger meteorite parent bodies and undergo melting and recrystallization. I will explain this later. Let's look at the last type of meteorites. Iron meteorites. 铁质陨石. It's 5% of total finds. And this kind of meteorites is just a piece of iron. Pure iron, sometimes with nickel. And if you cut through the rock, the meteorite, you will see this very unusual pattern. This in German is called the Wittmann-Steffen pattern. And this pattern is formed when this metal is allowed to cool down very slowly. So they are formed in the core of larger meteorite parent bodies, where the metal core is well insulated and cool down very slowly. So you see three kinds of meteorites. One is chondrites. Second is achondrites. Third is iron meteorite. Don't you see? This actually tells us the following story. Chondrites means the nebula material condense and just condense. They probably form a very small piece of rock. And they do not undergo some kind of plate tectonic. There's no plate tectonic in very small body of rock. And then they enter the space, they enter the atmosphere of the Earth and we find them. But for achondrites and iron meteorites, they are actually from a bigger planet-like, okay, we call it planet or asteroids, or parent bodies, 就是母体啦. And because they are bigger, they have more heat. So they form plate tectonics. And when they have plate tectonics and they start to segregate. We will talk about this in a few weeks. And the iron and silicate. This is iron and this is silicate. They no longer mix with each other. They start to separate. And later, this parent body, they break down, probably because of some impact. And the debris of this parent body enter the Earth. The outer part is the achondrites, and the inner part is iron meteorite. Then your question might be, how do you know there's plate tectonics in that parent body? Because you see this kind of mineral grains. It's angular, 就是有棱有角. It's like the volcanic rock on Earth. So we know there should be something like plate tectonics and some igneous 火成活动 to create this kind of rock. And then the iron, we will talk about this in a few weeks. They sink to the center of that parent body. It's like the core of the Earth. So with these three kinds of meteorites, we start to figure out what might be inside the true material inside Earth and also in the mantle. Because these meteorites are actually broken planets that enter our Earth. 就是它们是已经破掉的行星的碎片掉到地球上。So we know what could be inside us. Okay? So that's okay. So far we all talk about indirect evidence like a density or from meteorites. However, these are the science back in the 20th centuries. In the 21st century, science has already advanced a lot, and in fact, we already have some direct evidence of direct contact by sending some aircraft spacecraft into the space. And today I will show you some footage about Cassini, which is this spacecraft, and its voyage to Saturn. So if you are interested in the story of Cassini, you can find more footage at the website of NASA and also on the website of National Geographic. There's actually a 2-hour documentary of Cassini during its grand finale. I've actually watched that video, watched that documentary. So it's a very moving moment for us to see it crash into Saturn back in 2011. I actually wonder if you were born in 1997 when Cassini was sent out to Saturn. All right, I will probably, the following part is just storytelling, so I will talk about this next week. Let's do the summary that we have not been doing a while. All right. We will finally leave the field of cosmochemistry and enter the Earth. And to do that, we first need to talk about minerals. And we will talk about mineral chemistry, which is actually chemistry. So therefore, for Group A students, recall your general chemistry course. So please explain the following concepts. What is Pauling's Rule 1, Pauling's Rule 2? Coordination number, isodesmic, anisodesmic, mesodesmic. I have no idea what's that. So you have to read the textbook. It's all about how to build minerals. For Group B students, another list of terms. Aufbau principle, Pauli exclusion principle, Hund's rule, and then fill out the orbital configuration for elements in the table in the next slide, which is, recall your general chemistry. You need to fill in electron configuration. Okay, 1s2, 1s2, 2s2, 2p2, okay, etc. And also tell us the number of valence electron. And what's octet rule? And draw the octet of CO2. Octet rule is 八隅体. Remember? Okay, so you need to draw the electrons, dots. Okay, class dismissed.